The paper introduces the concept of uncertainty quantification for Data Shapley, a widely used method in machine learning to value data points based on their contribution to model performance. Data Shapley is rooted in cooperative game theory, where each data point acts as a player and the utility function represents the predictive performance of the model trained on different combinations of data. The goal is to distribute payoffs fairly among players, mirroring the equitable distribution of data values. The Shapley value, derived from the weighted marginal contributions of a data point to all subsets that do not contain it, has gained prominence due to its adherence to 4 desirable axioms with fairness interpretations. However, Data Shapley exhibits several limitations in practical applications. Firstly, its computation is intrinsically tied to specific datasets, making it difficult to generalize across different datasets. Secondly, it assumes a fixed dataset, which contradicts the dynamic nature of real-world data that constantly evolves and expands. To address these limitations, the authors establish a relationship between Data Shapley and infinite-order statistics, allowing them to quantify the uncertainty of Data Shapley with changes in data distribution from the perspective of statistics. This approach enables statistical inferences on data valuation, providing confidence intervals for the estimations. The authors propose 2 algorithms to estimate this uncertainty and provide recommendations for their applicable situations. They also conduct a series of experiments on various datasets to verify asymptotic normality and propose a practical trading scenario enabled by this method. This work aims to enhance the understanding of data valuation and facilitate more accurate data trading in the burgeoning data market. In the realm of machine learning and data science, data valuation is a pivotal problem that has garnered significant attention in recent years. The concept of Data Shapley, originating from cooperative game theory, is widely employed to assess the contribution of individual data points to model performance. However, it assumes a static dataset, which fails to capture the uncertainty that arises from data changes. This paper aims to address this limitation by introducing a probabilistic framework for Data Shapley, treating the valuation of a specific data point as a random variable. By leveraging the statistical property of infinite-order statistics, we can analyze the uncertainty of data values when other data or the data volume involved in model training changes. Our approach establishes a novel connection between Data Shapley and infinite-order statistics, providing a fresh perspective on understanding the uncertainty introduced by data variations. We justify the asymptotic normality of the Monte Carlo estimator of Data Shapley and provide statistical inferences for the estimator. This allows for a more nuanced understanding of data value in dynamic environments, potentially extending the applicability of Data Shapley to scenarios where data uncertainty is a critical factor. The paper is structured as follows. Section 2 discusses related work and our contributions. Section 3 introduces the basic concepts of Data Shapley and statistics. Section 4 explores the understanding of Data Shapley from the perspective of statistics. Section 5 delves into the asymptotic normality of the estimator and provides a detailed description of the hypothesis testing process. Section 6 proposes 2 estimation algorithms. Section 7 focuses on simulation studies and validates our theory through extensive experiments. Finally, Section 8 summarizes our conclusions. Our research contributes to the development of more adaptable and trustworthy data valuation frameworks, bridging the gap between static valuation methods and the dynamic nature of real-world data. By quantifying the uncertainty of data values, we can assist data providers in anticipating value changes in specific data points when other data is replaced with identically distributed data. Additionally, our approach aids data buyers in evaluating the reasonableness of sellers' data pricing in data trading scenarios. The paper discusses the concept of Data Shapley, a method derived from cooperative game theory that aims to quantify the contribution of individual data points to a model's performance. Data Shapley is defined as a weighted average of the marginal contributions of a data point to all subsets that do not include it. It adheres to desirable axioms such as efficiency, symmetry, dummy, and additivity, which ensure fairness and comprehensive value allocation in data valuation. However, the practical use of Data Shapley faces computational challenges due to its high complexity. To overcome this, Monte Carlo approximation is often employed for estimation. The Monte Carlo approximation formula for Data Shapley, denoted as nu, z, v, b, is given by the average of the marginal contributions to m randomly sampled subsets. This study introduces the concept of the Data Shapley distribution, allowing researchers to study the asymptotic properties of Data Shapley through the lens of infinite-order statistics. It establishes the asymptotic normality of the Data Shapley estimator and constructs confidence intervals, providing tractable formulas to quantify uncertainty in data valuation. This sets the work apart from previous research on the distributional Shapley value, which focuses on enhancing the robustness of data valuation against dataset variations. The paper also proposes two algorithms to estimate the asymptotic variance of the Data Shapley estimator. The double Monte Carlo and pick and freeze algorithms have distinct advantages. Double Monte Carlo can achieve higher accuracy than pick and freeze by increasing the number of samples, leading to higher computational costs. Pick and freeze reduces computation costs by elaborately designing the Monte Carlo processing but has less accuracy than double Monte Carlo. The paper conducts a series of comprehensive experiments to validate the asymptotic normality of the Data Shapley estimator and presents a significant case study to demonstrate its practical applicability. This section delves into the relationship between Data Shapley and infinite-order statistics, IOUS. It begins by introducing statistics, which are symmetric unbiased estimators for parameters of the form theta equals EP, H, x1, x's, where x1, xn are I, d. From an underlying population PAU statistic is defined as unequals, n choose s, 1 sigma h, she 1. Xis, with the sum taken over all combinations of S distinct elements from 1, n. The concept of statistics has been expanded to include situations where both S and H depend on n. The paper then discusses infinite-order statistics, IOUS, which arise when S right-pointing arrow infinity as n right-pointing arrow infinity. An effective approximation for IOUS, called incomplete infinite-order statistics, involves sampling a subset of n choose S tuples of indices and averaging them. This approximation is denoted as unequals, 1 per meter, sigma h, she 1, Xis, z, where the sum is taken over m randomly sampled combinations of S distinct elements from 1, n. The connection between Data Shapley and IOUS is established through the definition of nu S, z, b, equals n1 choose S, 1 sigma hs, s, z, where hs, s, z, equals v, s union, z, v, s. This expression represents a statistic of EDs, hs, s, z, with kernel h of order s. As s ranges from 0 to n1, nu S, z, b, is an IOUS of EDs, hs, s, z. The paper also introduces the distributional Shapley value, denoted as nu, z, n, equals 1, n, sigma EDs, nu S, z, b, which aligns with the distributional Shapley value proposed by Gorbani et al., 2020. This value is primarily introduced for two key considerations. Firstly, any changes to the dataset require recalculating all data values, incurring significant computational costs. Secondly, computing the expected values of Data Shapley across diverse datasets reduces variance, enhancing the stability of the values. However, the focus of this paper extends beyond this. It aims to analyze the asymptotic behavior of the infinite-order statistic in data valuation, providing a credible valuation interval as data volume n approaches infinity. Finally, the paper notes that accurately calculating nu S, z, b, requires enumerating all n1 choose S subsets, which incurs substantial computational costs for large n. An effective surrogate is to approximate it by a finite sample average, i.e., to sample m batches and compute nu S, z, n, m, equals 1 per meter, sigma hs, zij 1, Xis, z, where the sum is taken over m combinations of S distinct elements sampled from 1, n. This approximation represents an incomplete IOUS of EDs, hs, s, z, and can be further viewed as a Monte Carlo approximation of nu S, Z, B. A summary of symbols used in the paper is provided in Table 1. The research focuses on establishing the asymptotic normality of Data Shapley and its application in statistical inference. It begins by defining the Data Shapley and its corresponding U statistic, highlighting their relationship with the utility function in deletion stability. The concept of deletion stability is introduced, emphasizing its significance in the data valuation literature. The assumption of deletion stability is made, which has been widely utilized in prior work. The variance term is then defined, playing a crucial role in analyzing asymptotic normality. The theorem on asymptotic normality is presented, stating that the estimated value of Data Shapley follows a limit normal distribution with a mean of the true value and a variance of S2 zeta 1 S Z divided by n-1 under specific conditions. The results are partially supported by prior work, expanding on the conclusions regarding the variance of incomplete IOUS and its asymptotic normality. The research concludes by deriving the asymptotic properties of the Monte Carlo estimation of Data Shapley. The research paper discusses the statistical inference procedure for Data Shapley, a method used in data valuation to quantify the contribution of individual data points to the overall model performance. The authors introduce a new parameter gamma, which is crucial in establishing the asymptotic normality of the Monte Carlo estimate of Data Shapley. This normality is essential for constructing confidence intervals and conducting hypothesis tests on the mean value of Data Shapley. The Wald test statistic is defined to assess the significance of observed Data Shapley values, allowing researchers to evaluate whether the selling price given by a seller falls within the calculated confidence interval. To utilize these statistical tools in practice, consistent estimators for the mean and variance parameters must be established. While the sample mean can serve as a consistent estimate of the mean parameter, estimating the variance is more complex. The paper proposes two algorithms for estimating the variance, which are essential for instantiating the Monte Carlo framework in different ways. The inference process involves several steps, including estimation of Data Shapley using various Monte Carlo methods, construction of confidence intervals to quantify uncertainty, hypothesis formulation, statistical testing, and interpretation of results. These steps provide insights into the reliability and robustness of Data Shapley estimates, enabling researchers to determine the difficulty of calculating data values, anticipate changes in data value with replacements, and assess the credibility of sellers' data valuations. In conclusion, the paper presents a comprehensive statistical inference procedure for Data Shapley, introducing a new parameter gamma that facilitates the establishment of asymptotic normality. This allows for the construction of confidence intervals and hypothesis testing, providing valuable insights into data valuation and credibility assessments. The proposed algorithms for variance estimation further enhance the practical applicability of this approach, bridging the gap between complex research and concise, informative summaries for expert audiences. The double Monte Carlo method involves two layers of Monte Carlo simulations to estimate zeta 1, S, Z. It generates Monte Carlo samples to estimate the conditional expectation and performs simulations to estimate the variances. In contrast, the pick and freeze estimator simplifies the double-layer Monte Carlo into a single-layer Monte Carlo by leveraging lemma 6.1. This lemma facilitates the Monte Carlo process by converting the variance of the conditional expectation into the covariance of two components. Both methods estimate zeta 1, S, Z, but differ in their computational complexity. The double Monte Carlo requires extensive computational resources due to the two levels of Monte Carlo simulations, whereas the pick and freeze estimator has a lighter computational complexity. The research paper discusses the application of Data Shapley estimates for data valuation, focusing on the asymptotic normality of these estimates and the comparison of two proposed algorithms for estimating zeta 1, S, Z. The authors demonstrate the normality of Data Shapley estimates through histograms and fitted normal curves, showing how the distribution approaches normality with increasing sample size. They also compare the strengths and limitations of the direct Monte Carlo, DMC, and progressive fitting, PF, algorithms, highlighting the trade-off between accuracy and computational time. The paper further presents the process and results of hypothesis testing for data valuation using real-world data, including the construction and interpretation of confidence intervals. A scenario for data trading is proposed, illustrating the practical utility of statistical inference in real-world data valuation contexts. The authors validate their results using multiple datasets, including the cover type and fashion MNIST datasets, and demonstrate the applicability of their methods across various data sizes. The research paper discusses the application of Data Shapley values in various aspects, including data valuation, uncertainty quantification, and data addition tasks. It begins by presenting empirical coverage probabilities for estimated Data Shapley values across different data volumes, demonstrating the proportion of sample data values falling within their intervals. This is followed by a discussion on the theoretical quantiles and sample quantiles, highlighting the accuracy and stability of the estimated values. The paper then delves into the comparison of two algorithms, DMC and PF, for estimating zeta-1, S, showing that DMC offers higher accuracy at the cost of longer runtime. It also proposes a new method for data addition tasks, leveraging the 3 sigma rule to quantify uncertainty and estimate data value. The method combines Data Shapley with confidence intervals, allowing for the quick and effective addition of high-quality data. Experimental results on the fashion MNIST and cover type datasets demonstrate the effectiveness of this approach, outperforming other methods in data addition tasks. The research paper presents a comparative analysis of the Data Shapley and random data valuation methods in data addition tasks on the fashion MNIST and cover type datasets. Figure 6 illustrates the performance comparison, where Data Shapley plus 3 STD approach outperforms others in the fashion MNIST dataset, while Data Shapley 1 STD performs better in the cover type dataset. This highlights the importance of considering variability in data value estimation. In addition, the paper explores a transaction process dependent on confidence intervals, as depicted in Figure 7. The process involves the seller providing data points, the buyer assessing credibility by calculating value and confidence interval, and making a decision to proceed with the trade based on these calculations. The experiment using the cover type dataset, Figure 8a, shows that all sellers' pricing falls within the buyer's confidence interval, demonstrating the accuracy of the data valuation method. Similarly, the experiment with the fashion MNIST dataset, Figure 8b, also confirms the validity of the method, with the seller's valuation falling within the buyer's calculated confidence interval. However, when the labels of the top 5 data points are flipped in the fashion MNIST dataset, the confidence interval no longer encompasses the seller's valuation, and the buyer's valuation is significantly lower than the seller's valuation, Figure 8c. This experiment underscores the usefulness of confidence intervals for evaluating the accuracy of the seller's valuation and assessing data quality. It also suggests that buyers can leverage their own valuation of the seller's data to make informed decisions. Overall, the paper presents a robust data valuation framework that incorporates variability and confidence intervals, providing insights into the credibility and quality of data. The paper explores the concept of Data Shapley, a method for valuing data in machine learning, from the perspective of statistics. The authors derive the asymptotic normality of Data Shapley's estimated values, enabling statistical inference and confidence interval estimation for data value estimation. 2 methods for estimating limiting variance are proposed, with recommendations for their applicability. Figure 8 presents the results of simulations on real datasets, demonstrating the effectiveness of Data Shapley in estimating data values. The figure shows that the seller's estimates fall within the confidence interval estimated by the buyer, except when the labels of the first 5 data points are flipped, highlighting the importance of confidence intervals in establishing trust in data trading markets. The paper concludes by discussing the practical application of Data Shapley in enhancing the credibility of data valuation. The authors aim to extend these valuations to more real-world trading scenarios in future work, thereby increasing the feasibility of transactions. The references provided include works on statistics, probability theory, and machine learning, as well as papers on data valuation and pricing in data markets. These references support the development of Data Shapley and its applications in data trading markets. The author's contribution lies in the development of a robust method for data valuation, which can increase trust and credibility in data trading markets. By providing confidence intervals for data values, Data Shapley can facilitate more efficient and reliable transactions. The paper's findings have significant implications for the development of data markets and the valuation of data as a critical asset. This research draws upon a comprehensive range of prior works in data valuation, machine learning, and statistics, citing numerous seminal papers and authors. The authors acknowledge the contributions of Yongchan Quan and James Zhou, 2022, in proposing the Data Shapley framework for unified and noise-reduced data valuation, as well as Xiaobai Li and Srinivasan Raghunathan, 2014, on pricing and disseminating customer data with privacy awareness. Lucas Mensch and Giles Hookers, 2016, work on quantifying uncertainty in random forests via confidence intervals and hypothesis tests is also referenced, alongside Xiaoyue Niu et al.'s 2020-2021 research on online pricing with reserve price constraint for personal data markets and trading noisy aggregate statistics over private correlated data. The authors further draw upon Jian Pei's 2020 survey on data pricing, from economics to data science, and Shalev Schwartz et al.'s 2010 work on learnability, stability, and uniform convergence. The concept of Shapley value, introduced by Lloyd S. Shapley, 2016, is also crucial to this research. The paper also references I.M. Sobel's 2001 work on global sensitivity indices for nonlinear mathematical models and their Monte Carlo estimates, as well as Yanglei Song et al.'s 2019 research on approximating high-dimensional infinite-order statistics. Furthermore, the authors cite Siyi Tang et al.'s 2021 application of data valuation for medical imaging using Shapley value, and Zhihong T. Wang and Ruoxi Jia's 2023 development of the data Banzhaf framework for robust data valuation. On page 24, the authors reference N.C. Weber's 1983 central limit theorems for a class of symmetric statistics, Mengmeng Wu et al.'s 2023 variance-reduced Shapley value estimation, and Han Xiao et al.'s 2017 fashion-MNIST dataset for benchmarking machine learning algorithms. The paper also draws upon Jia Xu et al.'s 2024 work on machine unlearning, Tom Yan and Ariel D. Prokach's 2021 research on the core of cooperative games, and Cheng Ye and Chewei Lin's 2009 comparisons of data mining techniques for predictive accuracy of probability of default of credit card clients. Here is a combined summary of pages 25 and 26. In the appendix, the authors provide proofs for the Lindbergh condition and Theorem 5.1. Lemma 8.1 states that, assuming certain conditions on the function hs, the predicted tail behavior can be controlled, leading to the conclusion of Theorem 5.1. The proof relies on Hofding's inequality and the Kramer-Rao lower bound inequality. Specifically, the authors show that the probability of h1 s z z exceeding a certain threshold decays exponentially with respect to n, implying that the Lindbergh condition is satisfied. The authors then proceed to prove Theorem 5.1 by defining the Hayek projection of nu s z n ms minus nu s z. This projection is expressed as a sum of conditional expectations of the form E nu s z n ms minus nu s z n z, which can be further simplified using the linearity of expectation. The resulting expression involves a sum over combinations of S distinct elements from Z1, Zn, Z, and the authors exploit the fact that the subsamples are selected uniformly at random with replacement to rewrite this sum in terms of a binomial distribution. Ultimately, the Hayek projection is shown to equal S, n1, times a sum of h1, S, Z, Z, terms, which is a critical step in the proof of Theorem 5.1. The authors also define a triangular array involving the functions h1, s, z, z, and various combinations of S distinct elements from z1, zn, z. This array plays a key role in the subsequent analysis. For each variable in the array, the expected value and variance are calculated, leading to the satisfaction of the Lindbergh condition. This allows application of the Lindbergh-Feller central limit theorem, showing that the sum of variables follows a standard normal distribution. The limiting variance ratio of the incomplete statistic and its projection is compared, utilizing the relationship established by Blom, 1976. The limiting variance ratio converges to 1, indicating equivalence. The Slutsky's theorem and van der Waals theorem 11.2 are then applied to demonstrate that the difference between the incomplete statistic and its projection, along with the projection itself, converges to a standard normal distribution. This series of mathematical derivations and applications of theorems culminates in a comprehensive understanding of the statistical properties of the incomplete statistic, particularly its convergence to a standard normal distribution under certain conditions. The proof of Theorem 5.2 is presented in this section, which involves the application of the Lindbergh-Feller central limit theorem. To satisfy the theorem's conditions, it is necessary to show that the variance of the sum of the random variables converges to a finite limit and the Lindbergh condition holds. For the first part, the variance is given by 1 n gamma squared sum underscore s equals 0 caret n gamma 1 s squared zeta underscore 1 s z, which converges to a finite limit as n to infty. The Lindbergh condition is also satisfied, as the probability of the absolute value of the standardized sum exceeding any positive value, epsilon, tends to 0 as n to infty. Therefore, the first part of the theorem is proven. The second part of the theorem is proven by bounding the difference between the variance of the sample mean and the variance of the population mean. This difference is shown to be of order O sqrt n caret 1 nn gamma log n gamma plus 1 n gamma caret 3 halves and O sqrt n caret 1 log n gamma n gamma caret 3 halves, both of which tend to 0 as n to infty when gamma geq 1/3. Thus, the second part of the theorem is also proven. Finally, the Slutsky's theorem is used to combine the results from the first and second parts, yielding the overall result of the theorem. Sqrt n hat nu z n gamma m nu z n stackrel d 2 n 0 1. In the additional experimental results section, the authors provide empirical validation of their theoretical findings across various datasets, as detailed in Table 3. This study explores the application of double Monte Carlo (DMC) and Pathfinder (PF) algorithms in estimating the value of a given data point, with a focus on the normality of these values across multiple datasets. The experiment uses 8 different datasets, including cover type, fashion MNIST, credit card, vehicle, apps fail, IDA 2016 challenge, phoneme, wind, 2D planes, click, and CPU. Each dataset is tested with a training set size of 100 and gamma equals 2/3. The first column of figures 9 and 10 presents the confidence interval graphs for the corresponding datasets, demonstrating the normality of the estimated values. The second column displays the QQ plots for these estimated values, showing a strong correlation between theoretical and sample quantiles. The third column illustrates the empirical coverage probabilities, which are nearly 100%, indicating that the confidence intervals constructed using the DMC algorithm provide accurate estimates. The runtime and accuracy comparison between DMC and PF algorithms on the fashion MNIST dataset is presented in Figure 11. It can be observed that as the number of inner loops in DMC increases, the running time increases rapidly, exceeding that of PF. However, the estimated values tend to become more stable with increased T, indicating improved accuracy. The analysis demonstrates the effectiveness of the DMC algorithm in estimating the value of a given data point, providing accurate confidence intervals and empirical coverage probabilities. The study also highlights the limitations of the PF algorithm in terms of runtime and accuracy, particularly when dealing with larger datasets. This research contributes to the understanding of statistical inference in machine learning and the development of efficient algorithms for data analysis. The analysis of estimated values for phoneme, vehicle, and wind datasets with a training set size of 100 and gamma equals 2/3 is presented in Figure 10. The first column displays the confidence interval graphs for the datasets, illustrating the accuracy and precision of the estimates. The second column provides the QQ plots for the estimated values, which demonstrate that the observed quantiles closely follow the theoretical quantiles, indicating a good fit between the model's predictions and actual outcomes. The third column depicts the empirical coverage probabilities, confirming almost 100% coverage, suggesting that the model's confidence intervals are well calibrated. In Figure 11, a comparison between the DMC and PF algorithms on the Fashion MNIST dataset is provided. The left panel, Figure 11a, shows the runtime comparison, with t equals 100 for both algorithms and varying inner loop counts for DMC. The running time of DMC increases rapidly with the number of inner loops, far exceeding that of PF. This indicates that while DMC may provide more accurate estimates, it is computationally less efficient than PF. The right panel, Figure 11b, shows the estimated values of zeta 1 s using DMC with varying t. As t increases, the estimated values become more stable and accurate, suggesting that increasing the number of iterations improves the precision of the estimates. This highlights the trade-off between computational efficiency and accuracy in the context of DMC and PF algorithms.